So this next method only applies to poles of order more than 1, and it applies when your phi, you notice, has a parameter which I'm going to call the parameter a. So it's a function of a and z, and you notice that your phi has the form of a derivative of something else. Now that something else you hope is going to be well, for example, if it's a if you're after a pole of order 2, then you hope that it's the derivative of something which has a pole of order 1. Then basically what you can do is, it's easy to find the residue of a pole of order 1, a simple pole, and if it turns out that the function you're after finding the residue of can be obtained by differentiating with respect to this parameter a, then this is a particularly quick way of getting the answer. This will become clearer with an example, but what we'll do now is actually just show quickly why this result is true. So we suppose that C is a contour which encloses only Z0. So there's no other singularities inside the contour, only Z0, which means according to the residue theorem, this integral here, this contour integral around C of phi, is just equal to 2 pi I times the residue at Z0 of phi. Then what we do is we differentiate both sides with respect to A. We're allowed to differentiate through the integral, so we end up with this. Okay. But this thing here, I can also apply the residue theorem to this. Okay, so the residue theorem applied to this will give me the residue, 2 pi I times the residue of d phi by dA evaluated at Z0. So that means these two things are equal. This thing here equals this thing here, which is what we're trying to prove.